Hello, good people. Welcome to video number one of topic 6.4. It's actually the other part of 6.4, which is the second part of the fundamental theorem of calculus. So you might recall, and I'm going to scroll this over, you might recall that we've done the first part. So part one of the fundamental theorem of calculus says that if I'm taking the integral from a value a to a value b of some function, then if I can find the antiderivative of little f, so if I can take the antiderivative, and I'm going to call it capital F. So think of this as the original function, and then this is the derivative. And if I take the integral of this derivative, and this would be the antiderivative, I can evaluate that top limit in the original function, the antiderivative, minus f, capital F of a. So this is what we've been using to evaluate definite integrals. And we're going to need this part of the fundamental theorem to show the second part of the fundamental theorem. So we're going to come back to this idea. Don't you worry. But we're going to start by talking about what I call area functions. And I call these area functions because this function is defined as an integral. So I'm looking for the area. I'm looking for the area of f of t, under f of t, starting at 1 and ending at whatever x value I give you. So just as an example, g of 1 would equal the integral from 1 to 1 of f of t dt. Now, I don't know what the graph of f of t looks like. I don't know what the equation of f of t looks like. But I know that if I start and I end at the same value when I'm taking an integral, I'm not accumulating any area. So therefore, my answer would be 0. So if I were to come over here and make a table of x values and g values, or g of x values, I would know that when x equals 1, g equals 0. So when my input x value is 1, my output g value is 0. But if I were to do g of 2, well, then I'd be looking for the integral from 1 to 2 of this function f, little f. And now I kind of need to know what it is, right? I need to know either the equation or the graph, because now I am accumulating area from 1 to 2. So this is going to be some kind of an answer. I'm going to call that, I don't know, a for answer. So therefore, when my x is 2, my answer is a. So it's another value. It's not 0, right? But I could continue to do that. And in so doing, I create a whole other function, the function called g, the function whose purpose is to find the area under the curve of f, starting at 1 and ending at whatever the x value I tell you to end at. That's what I call an area function. I think some people call it functions defined by integrals, because this is a function defined by an integral. Cool. So we will be looking at these functions, but specifically, we're going to want to take the derivative of these functions. So if g is a function, well, then I can take a derivative just like I can take the derivative of anything else. And so when I look at this, suppose a is a constant. So a is some number like 1 or -1 or 5. And u is a function of x. So u is a function of x. So it could be like x to the third. It could be x. It could be e to the x. It could be any function. If g of x is defined as this definite integral, can we find the derivative of g of x? Well, yes, but we're going to need to use the limits of integration first to evaluate the definite integral, remembering that the bottom limit is a constant. So this is a constant, and this is a function of x. So that's going to be weird, because we're used to seeing a number on the bottom and a number on top. But here, the one on the bottom, the lower limit is a constant, but the upper limit is a function of x. And then, after we take the definite integral, we evaluate the definite integral using the first part of the fundamental theorem. Then we're going to come back and we're going to differentiate the answer. Why are we going to differentiate the answer? Because we're looking for g prime. So we're going to take the derivative, take the integral by using the first part of the fundamental theorem, and then we're going to take the derivative, because then that's going to get us what we want. We want to find g prime, but we need to rewrite or evaluate g of x using this definite integral so that I can take the derivative. So how do we do that? With part one of the fundamental theorem. Part one says, hey, if you can find an antiderivative of little f, and I'm going to call that capital F, then evaluate the top limit minus evaluate the bottom limit using that antiderivative, and then subtract those answers. Remember, the derivative of capital F is little f. So that means, maybe I'll make a little note. Capital F is an antiderivative, right? So the derivative of capital F is little f. That's how we found the antiderivative. Okay, we did step one, but now we're going to have to take the derivative. Okay, well, if I'm going to take the derivative, I'm going to take the derivative of the first part and the second part. Well, the derivative of the first part would be f prime, except as I go to write the next part, I remember u is a function of x. So it's like an inside function. So then I'm supposed to multiply it by u prime, because I have to do the chain rule if I'm taking a derivative with an inside function. And u, we said, is a function of x. So I'm going to take the derivative of the outside with the inside still in it times the derivative of the inside, minus the derivative of f of a. But a was a constant number. It was just a value. So when I do f of a value, I'm going to get a value, and the derivative of that, the derivative of this, is just going to be 0. And so therefore, the only thing that I have left is this. So what did we do? We used the first part of the fundamental theorem to evaluate and change, I guess, the way g of x looks. G of x looks like a definite integral, but if I do the fundamental theorem, now I have a difference of the top limit minus the bottom limit evaluated at the antiderivative. And then we took the derivative of that because we were looking for g prime. So I rewrote it in purple here, but then I took the derivative of each of these, remembering that the second part is a constant, so it goes away, and also remembering that this has an inside function, so I have to use the chain rule. But wait, didn't we say capital F? We said it over here. Capital F is the same thing as little f. So then this equals little f of u times u prime. And this takes us to one of the most fundamental ideas in calculus and unites both parts of calculus, the differential part and the integral part. Where we take derivatives and we take integrals, it turns out they're related. How do I know that? Because when I took the derivative of an integral, right, that's what we were doing, taking the derivative of this integral function, the answer that I got is just whatever I was taking the antiderivative of, with the upper limit plugged in and then multiplied by u prime because it's a chain rule. So this leads us to the idea that derivative and integrals are inverses of each other. And that also leads us to the second part of the fundamental theorem, which says when you take a derivative of an integral, the derivative and the integral are going to undo each other, and you're just left with the function f, or whatever the function is inside in the integrand. But with the top limit evaluated inside, and if I have an inside function and I'm taking the derivative, I'm supposed to multiply by the derivative of the inside. This might seem like it's a little weird, but when we see the examples, you're going to see that it's going to flow very nicely. But what you need to remember is when you take the derivative, but this is only when you take the derivative of the integral, they're going to undo each other. I'm just left with the function evaluated at the top limit times the derivative of the top limit. That's the second part of the fundamental theorem, and that's the connection that we need to show that these two operators are really inverses of each other. Taking the derivative, taking the integral are opposite functions of each other. So we're going to use the second part of the fundamental theorem whenever we need to take the derivative of an indefinite integral with variables in the limits. So if you see variables in the limits and you have to take the derivative, we're going to use the second part of the fundamental theorem. The nice thing about it is that we can do this without having to integrate or differentiate whatever the function is itself. So notice, we're never going to have to worry what the function is, because all we need to do is substitute this top limit in there, and then multiply by the derivative of whatever you plugged in. And then make sure that you're using the chain rule and you multiply by the derivative of u. This is the part that most students forget. They will plug in the top limit. That's awesome. But don't forget to multiply by the derivative of that inside function you just plugged in. So in the next video, we're going to look at some examples, but this is going to be the driving force to some of the most popular free response questions on the AP exam.